Hello everybody, Root Beer here. I thought I would do a little more in our GeoGebra environment. So we've constructed some nice regular n-gons and even some regular 2 n-gons. We've done things like the Equilateral Triangle, a regular 3-gon, and the regular 5-gon. I've got plans to do regular 17-gon. Yes, I have decided I'm going to do that even though it's a little lengthy. But I thought I'd show you, so the 3, the 5, the 17, I've mentioned the 257 in the past, and then there's another big one whose number I always forget. It's something like 2 to the 31 plus 1 or something to that effect. I can't quite remember. Oh no, it's 2 to the 16 plus 1. What's 2 to the 16? Bah. Anyway, entirely immaterial. So we've got, these are based off of numbers called Fermat primes. And if you, it's a nice result, although it takes some Galois theory, just some more advanced math. But it's a nice result to or at least the way I saw it was with Galois theory. It's a nice result to show that if you got a Fermat number, which is a number of the form 2 to the 2 to the n plus 1, and it happens to be prime, you can construct a regular convex that many sided polygon. So 3 is 2 to the 2 to the 0 plus 1. Then we've got 2 to the 2 to the 1 plus 1 for 5. 2 to the 2 to the how do you get 17? 2 to the 2 to the 2 plus 1 for 17. 2 to the 2 to the 3, so 2 to the 8 plus 1 for 257, and then the 2 to the 16 plus 1. And those are the only Fermat primes we know. So we can get the regular 3-gon, the 5-gon, the 17-gon. We can't get something like a regular 9-gon. And this can be proven, although it's beyond doing simple compass straight edge stuff, which is what I've been doing. But we can also combine these. And so the only constructible polygons, and this is a nice result, is anything that has any n where n has a prime factorization of the following form. Whatever power 2 you like, times at most 1 3, times at most 1 5, times at most 1 17. And you can have at most 1 prime factor being a Fermat prime of each type. So you can have a 3 times 5 times 17 gon. So that's a 15 times, so that's a 255 gon. You can construct one. And you can do 4 times a 15 gon. So you can do a 60 gon. That sort of stuff. So any power of 2, but you can only have 1 3 in your factorization, only 1 5, only 1 17, and so on. So I've shown you how to do the 3, I've shown you how to do the 5 and the 17, but I haven't shown you how to sort of combine them a little bit, and I thought I'd do that now. It's also going to show you another way to construct the equilateral triangle. So when we did the Pentagon, and when I do the 17-gon in the future, you have to start with a given length, as we always do. So an AB, and we'll get a segment here. But we don't use this segment for the side. Okay, so we have with the equilateral triangle, we have with the square, when we did the hexagon, we use this length. We didn't quite do this with the 2-gon. Maybe I'll show you guys how to do it with a particular length, or get a particular side length. But the point is, with the equilateral triangle, we use this length, but with the Pentagon, we use this as the radius of the circumcircle of the Pentagon. So what we want to do is get both. We're going to make a regular 15-gon here. We're going to get both the equilateral triangle and the Pentagon with the same circumcircle. So we have to construct a Pentagon, yes. So we're going to do that. But we also have to construct an equilateral triangle inside the same circle. Okay. And so we're gonna talk a little bit about how to do that. Anyway, we'll pick. I guess we'll do the equilateral triangle first, since you have seen the Pentagon already. So the equilateral triangle is actually pretty quick. You just get the bisector of A and B, and we use both of these points rather than just one. But then we get the other point over here, and now these 3 give us an equilateral triangle. And we can connect them up to make a orange equilateral triangle. So now we got an equilateral triangle in the circle whose radius is AB. Great. We're going to zoom in a little bit. Now let's get a pentagon. And we know how to do the pentagon. We've seen that before, but let's get it in the same circle here. So we need perpendicular line through A. Okay. And we've already actually, thanks to our work, we've already got the halfway point between A and B, although we would have needed that next. Why is it not? It's not happy with me. Why is that? Usually goes blank. Is it point on object that I want? No. What is going on with my points? This hasn't happened before. Yeah, they're going blue. Blue usually means I've done something and it's not technically on the figure that I want it to be on. This was working fine a moment ago. We still... That one's fine. Why is this one so much bigger? Do I have to hide something? What is this? Sorry about this. I haven't encountered GeoGebra doing this sort of nonsense before. Okay. So there, I think it's fine. We don't really need the line anymore. So we need this intersection up here. Fantastic. Okay, so now we've got an angle that we need to bisect. Okay, and then it's the intersection point over here. And then we just want to get a perpendicular line through that. So let's clean up a lot of this. Okay. So perpendicular line. Oh, we don't need that one. We need this point up here. Those go through, and then if this is all worked out, and I've thought it's worked in the past before, and it just it did not for some reason give me a pentagon. So let's just hope this works. It usually happens if I've got some point somewhere, and I think it's on an intersection, but it's actually not. That's usually what happens to cause this to mess up. We'll hide everything that we don't need. So now in theory, I can take these guys in circles around, and I should get my pentagon, and I do. Okay. So you can tell it is a pentagon because between any 2 points we can get a radius of a circle, and that circle will intersect a third point. So you can tell we've got the pentagon. That's really how you can tell you've got any points evenly spaced to make a regular whatever-gon on a circle. So what shall we make the pentagon? What color should it be? Somebody out there thought brown, so let's do brown. If it wasn't you, that's okay, it was somebody else. So, we've got the brown pentagon and the orange equilateral triangle. And this sort of technique here would work for anything. You could put the pentagon and get the 17 gun in there, or the 17 gun in the triangle, that sort of thing. If you want to be bold, do the 257 gun and the pentagon or something like that. Doesn't matter. So what we're going to do, these points on the two figures, these are actually going to be on our what do I want to say? They're going to be on our 15 gun. Now, we do have a little bit of a problem. As you can see, if these exact points were on the 15 gun, we'd have a very small 15 gun indeed. What we actually need to do is translate our pentagon so that he shares a vertex with the equilateral triangle, and that's something we've got to do. Okay? But this amounts basically just to reproducing an angle. Okay? So, how are we going to go about doing this? What do we want to do? I'm trying to think. Rather than translating just in the sake of time, I think it would be a little better if we just constructed them originally so that we did it. So what we'll do is just take a bit of a shortcut and get these points. You can do it. I just don't want to go through the bother of rotating the angle so that it lies symmetrically around the whole thing. So we'll just use this length here, so we got another diameter. So we'll create the equilateral triangle again. So we already got that one. We get this one here. Oh yes. There we go. Because we doubled up on the circle accidentally. I say we, I meant I doubled up on the circle accidentally. There we go. So now these points give us our equilateral triangle. I made that dot out of habit. And this point up here is going to give me the rest of the triangle. So there, crisis averted. I don't have to make this video even longer. And we used orange, right? Okay. So as I was saying before, these vertices, now that at least two of them coincide, these vertices are going to give us the vertices on our regular 15 gon. Oh gosh, what did I do? I want to hide that, not delete it. Okay. So these vertices there'll be more vertices, but now if we imagine our regular 15 gon, behind a line of the pentagon, we're going to have sort of, I'll just use the light purple, we're sort of going to get 3 of these, because we have 15 in total, they have to be evenly spaced, so we're going to get 3 edges of the 15 gon. And behind a side of the equilateral triangle, we'll get 5. So overall, so if we sort of imagine it this way, we can see, well, we're going to sort of get 2 edges in between here. We'll get one here, and then sort of we'll get 3 more in here, that sort of thing. So this is me being inexact, but this we just sort of visualize our 15 gon. And so you can really take any pair of, so an adjacent pentagon and adjacent equilateral triangle point, and just sort of rotate them around, as long as it's not the common point. So like we could take this this distance here and just rotate it around, as you've seen me do, to create the pentagon, and that'll get us the regular 15 gon. And you can take anything. The 1 will do just fine, because these points are going to be adjacent on the regular 15 gon. Or you can be a little fancy And so I'm going to take, these two differ by 2 edges of the 15 gon, but 2 and 15 have a greatest common denominator of 1. So as long as I keep taking this around and around, I'll eventually get all 15, because the GCD of the 2 in between here and the total 15 gon means we will make it all the way around. And if you found one with the 15 and 4, that would work fine. I think I mapped it out, and the 17 gon and the 5 gon, there'll be a break between 2 that you can capitalize on. But there's some others. I mean, you just keep going around. So now we're back, and we've got our first set of 3. Well, sorry, second set of 3. Oh no, third set of 3. On the of consecutive corners of the 15 gon. Okay. So we keep going. And we can fill the whole thing out. But we have to choose a pair of vertices on the opposite. They can't both be on the Pentagon or both be on the whatever gon. They have to be on on different polygons. And then you have to pick 2 that differ by a number of edges on the total A times B gon that would have a GCD with AB. Okay, so there's all 15 points, and isn't that a lovely sort of kaleidoscope looking thing there? I feel like we're missing some down here. We don't actually need them, but there we go. There. So now the whole thing's done. That's quite pretty, even if we don't have the Pentagon and the given line in there. But we'll get rid of them all, and then we'll connect up and make a 15 gon. And as I say, you can do the exact same construction, do the 5 times 17, and get the 85 gon, regular 85 gon. And then use our 2n gon technique to get yourself 170 gon. So I'll get the segment tool out. I'll use the cyan. It's a little brighter, it stands out. We have ourselves a 15 gon. So this is the biggest one we've created to date. I'm going to get the regular 17 gon in another video, but it takes a long time. I did decide I'm going to do it, but it's going to take a while, so it gets its own video. Now we can get rid of the circumcircle if we like, and we can get rid of really just everything. The Pentagon and the Equilateral Triangle. You have to get them in the same circle, and as I goofed a little bit at the start, you do have to get them sharing a common vertex. But there we go, and this regular 15-sided polygon depends only on the A and B we started with. Fantastic. So, have fun constructing those, and I will see you guys in a future video for more.